哦。你可以回台湾吗？
哦，真的没有，今年没有。
哦，所以你要到还是啊？那就去我们这里。没有啊，出去玩没事。还是把所有的带去住吧。带了5个。啊。2啊，1啊，对啊，还有谁？还有那个成都的什么？
不是监狱。
是总务是啊。
哦，所以他是特别跑回来。
啊，那个不是监狱，那个是。我也另外一个。我也是刚跑回来，我上周1才回来，明天就走。回北京。对啊，我周1才从北京回来，然后明天就回去，就为了太夸张了。对啊，就是为了凑在一起，凑完才能回去。而且按这个把机票钱给他们扣了，我就先飞法国，你知道吗？先飞法国。对啊，他等于讲，先飞法国，在法国待6个小时，再飞北京。下回我们先从北京飞法国，然后飞法国待6个小时，再飞1个月。他管得很严，管得很严吧？他会算你，他会调到最便宜的票。太夸张了，原来这个风格。
到处选。
是啊，要去开会的时候。
我看他自己店在看的话，然后就想买。
我天天买东西，我也经常看买东西。他就是我在他是要什么评论我忘了。我在Google 的时候，他3个月卖了2个车，买了2个车，买了1个相机，卖了1个相机，买了3个镜头，卖了4、5个镜头，他买了自行车，卖了自行车，然后他买了好多衣服。对啊，他这个也是刚买的呀。没有，这个没有了，这是刚买的。
去年秋天他一台。
这不是这个。
不是这个。
他1年前他买了4个相机。就是买了之后天天找我怎么跟老婆解释。
可是他会卖掉吗？
就要他必须卖掉才能跟老婆解释的。他买了一个1000多的，他买了一个1000多、1700的相机。他呢，原来相机是送一个打印机给他的，他把相机卖掉，他说打印30公斤。我在中国时候我们需要打印，然后我们抬着头来费力也抬过去。但是他在加州卖不掉，因为所有人都买了那个打折的，那他还把它扛回了一个包卖，然后那里卖了300块钱，他把自己以前的相机卖了400-500块钱。
这样折旧没有？
对，他1000的相机卖在900块钱，只剩800块钱，这个老婆说800块钱买个相机，老婆就 OK 了。对。抽的，就开会他说不要批评。
然后他好像就觉得他们才好意思。
上9天，因为跟日本所教的。对啊，挺喜欢投资的东西。就开会都不给做个非很深。山深了，没什么？聊天很水，我们不给 ，SC 不给，SC 我不知道。
我觉得感觉就是老师给。
对啊，还是想办法去。然后这样找关系找staff，天天在站台。这样你们那台阶怎么去啊？跟我们报关一下。我这冰板和他们之前就是打个电话给他们。对啊，这种事情。对啊。今天下午开始吗？几点？差不多吧。不来了吗？啊？不会来。不会来。
没有，他是叫我结束的时候把这些东西
你录的像我也不能用，我不讲。I don't really care. He's so just fell. Yeah, they're not going to.
没开。
Okay, let's start so you can have a good weekend. So today we will talk about three things. One is that we talk a little bit about stochastic gradient descent and how to distribute that things. The second thing, we will have a very brief look at the implementation, how primary server works. Finally, I will show you some demos. Let's start with HGD. So the basic idea of HGD is quite simple. Okay, so instead of have the whole training data for the gradient descent, the HGD can only look at one example. So this is the algorithm show that for iteration time to 1, 2, 3, 4, each time we pick up examples and use that examples to update the model. So that is, if you choose example I at time t, now the first thing you want to do is that you compute the gradient over this example and update the model by the kind of model minus learning rate times the gradient on this example. So this is the basic idea. As you can see, the cost of each iteration is quite small because each time you only catch a row of the training data. And it's often converged very fast comparing to some batch algorithms. Comparing to the gradient descent, each iteration, the SGD may make a little progress comparing to if you get the same data. But given the same time, SGD may run a lot of more iterations than batch SGD. So even that you make a little progress each time, but you may run 1,000 times more iterations. So you may still win. That is a huge advantage of SGD. Is that okay? There are also some serious aspect about what is SGD good at. So the not so good thing that just like coordinate descent we talked about yesterday, SGD is a sequential algorithm. That means each time you process an example, you need to wait the previous example have been processed. That is, the model has been updated. If not, you should be wait. So just like coordinate descent, it's really hard to distribute like the SGD descent. But because that two algorithms have very similar workload. So for the coordinate descent, each time you process column by column. SGD process row by row. So the idea to parallelize the coordinate descent also applies here. So we introduce two ideas. One is that let each machine process one example, and these machines process at the same time. So here's the figure. So each machine maybe have a part of the data, and each one at one time process one example. Compute the gradient, send the gradient to the primary server. So on this case, if you have n machines, the delay should be n-1 because each machine didn't get the update from the rest n-1 machines. Remember that for the coordinate descent, if the features are not so correlated, so it's quite safe and it's perfectly fine if you update several features at the same time. But for the coordinate descent, you need to assume the examples are not so correlated. So two examples not correlated if the non-zero features of these two examples are different, so that there's little relationship between these two examples, so you can update at the same time. But generally, it's not true because remember that we have, for the sparse data, we may have very dense features. So a lot of examples, we have hit this feature. So on this feature, example correlated. So that assumption for coordinate descent cannot apply to SGD directly. So this is a hard thing. The second, another slightly different model is that instead of compute the gradient, send the gradient to the server, you can let a group of workers form a group. So it's run individual SGD here. So this group have all the process data and have a complete model on here. And this group can update the model. If you want to exchange the model between different groups, you send an update of the model to the primary server. And this is what Google Brain did, and it's perfectly fine for the system performance because each worker group works individually. And you can add a group as you like, and you can throw some group away. But the problem is still here because all these things model the same, update the same model. They have some correlation between them. So if you have a lot of machines write the same thing together, just like you write the entry with a multi-thread without guaranteeing everything. So nobody knows what the result comes from. So the problem here, if you have a lot of groups, it may affect converge rate. In practice, we found that if we increase the number of machines by 10 times, and you count how many times you need to go to reach a particular object function, you find you only have two times speed up. So it's not worse, but the things are different for Google. Google has a lot of machines. He really cares about how many time I need to get this thing. So I do not care about the resources, but I care about the time. So you can use this one, but for us, we do not have so many machines. We are not Google, so in practice, if we run these things, you should have a concern about it because 10 times machines, 2 times speed up. The second idea is very likely to the broad quotient descent. That is, rather than process one example at the iteration, we can process a block of examples, just several examples. So we can show that converge rate, here's the converge rate. And because each iteration you have a large workload than the standard SGD. So you can run multi-thread or distributed implementation within this mini batch, just to use the technology we have been discussed yesterday. And the only problem here is that you want to increase the mini batch size because you want to increase the workload of iteration so that the cost of multi-thread, cost of distributed computing can be comparing to the workload can be minimized. But the problem is that if we increase the mini batch size, you may decrease the converge rate. On this training case, the mini batch size is as large as the training data you have. That is standard gradient descent. So as you know, SGD is faster than gradient descent, so that means your converge rate goes down. Okay, so but you can do slightly better things. So let's first look at the overhead of a mini batch. So there's two overhead here. One is that the data may be on the disk, maybe on the distributed file system. So each time you need to read the data from disk. That's one overhead. As you know, read disk is much slower than read from memory. Secondly, you need to communicate the gradient or the model after the mini batch size. So you read disk communication over network. So maybe that two overhead dominate the local computations. Here's the nature idea that given you have already paid overhead for the mini batch, why not do better in this mini batch? That is, rather than get the data, calculate the first order gradient, update the model, and throw the data away, we can do more things here. So here's one example. So if the data you have and you solve the object function over this data directly. So you minimize the object function over the mini batch data you have. And it solves a small problem. This problem is a single machine. You can run on single machine. It's on memory. So you can run complex, sequential, but fast algorithm on these things. And because this is just a part of data, if you too fit this data, you may overfit the model because you have some noises. So how to do that is that you may add a regression here to guarantee that you do not go very far away from the previous thing you have. So you want to fit more about the mini batch you have, and you guarantee that you do not go far away. So if you solve this problem each time on each iteration, you can guarantee that the converge rate can be increased, and the converge rate is improved compared to the standard mini batch size. In practice, you don't need to solve this problem exactly. You can solve by some, for example, earlier store. For example, you can pass the data a few times by gradient descent, or you can pass the data, the mini batch, a few times by gradient descent. So for example, 10 times, or maybe 5 times. So I give some experiment here. So the first experiment is that on 2 data sets, fix the number of examples we process and increase the number of mini batch size. So for the general SGD, for the standard SGD, if we increase the mini batch size, given the same example you have, you decrease the number of iterations you have. That means it goes wrong, something wrong here. But if you run the quantity descent, solve the sub problem here, and you increase the mini batch size, the impact is very little because you take more advantage for the large mini batch size, and even you can get more from here. The second experiment shows if you get things to a distributed version. So if you run 12 machines and fix the running time to be 1,000 seconds, here's the thing you have got. You increase the number of the mini batch size, and you find the object function you get is decreased. That is, a large mini batch size increases performance because that reduces the number of iterations and you reduce the number of discrete computational network communication. So, and given the 1,000 of running time, you increase the percent of effective workload you have. So you can make more progress on here. So we give a quick conclusion here. Stochastic gradient descent is widely used. And I think now every other algorithm for them, because if the problem is quite complex, the only thing you want to have is how to compute the first order gradient of the first order gradient. So for example, if you have very complex deep learning or very complex object function, you maybe have a way to compute the first order gradient. So you can just simply run SGD. So that algorithm is the first one you may want to have a try if your program do not fit onto some standard settings. But distributed the SGD is more difficult than coordinate descent because the examples are more correlated maybe. And I think this is very active research here because for deep learning we really have that problem, and we really have problem to scaling deep learning for the mini batch SGD to a very large scale size. So the most economic way here for deep learning is that you have multiple GPUs, not so many machines, and so that you can enjoy some fast bandwidth and fast small delays, so you can run things. But it is a problem if you go a large model. So next I'm going to show. Let's have a look at how primary server works, and then I show you some examples. So still the problem, given training data, given the model, want to train something. But things different here, the model weight may be very large, so that you cannot be stored on a single machine. That as the experiment showed yesterday, we have about 60 billions of example features. So it's a huge model, so you should put on several machines. That is model partition and data partition here. So for the primary server, now you have two groups of machines. One's a server, one's a client, one's a worker. Each server, so a worker can communicate with the server. For example, push the gradient ahead to the servers, and also the server can communicate with the gradient, with the worker machines. For example, you have all these worker machines want to talk to the server. So give me the updated model. In fact, this is also your communication. So next, how to implement the gradient descent? It's quite like what we have been discussed before, but the only two things are different. One that there's several machines stored in the model. So this is several machines here. It's not a single machine. Secondly, what you want to care about is that this model, the worker maybe cannot put this model in its own memory. So because you have a huge model, maybe you cannot put that on memory. So this is a problem. But luckily, if you really have a large parameters, that means the data can be very sparse. Otherwise, it's not possible to compute on this data. So if you have very sparse data and each worker only get part of the training data, it's more likely that that training data have all these parameters you have. So what you want to do is that the worker only need to capture the entries of the model that have been shown on this training data. So if this feature do not occur on this training data, I don't need to catch this one. We did some experiments to show the exact numbers. So we randomly partitioned the examples to workers. And if you have only one worker, you need to catch the whole train, the whole model. Yeah, that makes sense. But if we increase the number of workers to 100, each worker only need to catch about 7.8% of the model. And if we increase this one to 10,000 workers, this number goes down, goes about 0.1% of the data. So even that you have a really large model, but you can increase the number of workers so that you can always fit onto the workers flow continuity. Okay. So this is how we deal with very huge model. Next, because on the real data, the feature ID has that is an identification of the feature, maybe a string. For example, for the unground features, maybe just the unground, or for the session feature, maybe just a session of the click patterns. Or you can do some hashing to hash to a random 64 bits or 128 bits integers. You need so large integers because you need to guarantee the features are not conflict too much. And this is, if you have a map the things onto small integers, you maybe have high conflict rate. And it maybe do not affect how you train the things. It's okay. Just like Alex has discussed, if you have it, using hashing to map the huge feature onto very small ones, it's okay on the performance. For example, on the accuracy, on the AUC, is perfectly fine. But the problem is that we find it has something wrong if you really deploy that model, because you need to rank in the things. You do not really care about how you classify the things. You care about the numbers, because for each ads, you need to predict the probability will be clicked. This is numbers, and you need to rank in these things. Even that you have slightly precision, not good enough. The ranking can be different. So it can be affect the things. So in this case, you need to have a large integers. And we hope that our model can keep this large integers different. Given that thing, the problem is that how to assess given a feature ID, how to get the entry from the model. You have one natural thought is that, okay, use a hash map. Why not? Because it's a general solution. Give a key and I give the value. But it could be slow because you need, for hash map, you need to have several memory random access. Remember that for the sparse nature computation, it's a memory assessment that dominates the performance. And for the hash map, maybe you have several if and else things, so you have a lot of branch mistakes. So using the hash map things is about, I think in practice, about 5 times slower than using a general array thing. So I think we can do better because that thing really matters local computation. What you can do another way is that you can localize the global ID onto a local ID. That is, each worker machine get a part of the training data, and you first count how many unique keys you have on this data. You get all these keys and map this keys onto a local training feature ID. Start from 1, 2, 3, 4, and it continuous. So next, you can make a compact representation of the training data. That is, you map the global key onto local things. Now instead of store the model on the hash map, now you can have just using an array to do the things. So if you do that way, for the local computation, you can just use what you are familiar with. So it's an array, it's a sparse matrix. So we have discussed how to do that thing on the first day lecture. The only thing you want to map is that you need also to keep the global keys, because if you want to communicate something between different machines, you need to bring this keys with you. So the advantage of the localized key solution is that you save some space. Rather than store the strings or large integers, now you only have 32-bit integers. So at least you save half of the space. Next, okay, you use an array to store the things. It's much faster than the hash map. The third and the most important thing is that you can reuse some existing libraries. For example, you can use eigen3 and write things like MATLAB style. The disadvantage is that you need to do some pre-processing. You need to convert the global ID into local ones. This is one overhead. The other thing that it's only suitable for some applications. So if you have the trained data at the beginning, you can do it. But maybe for the online learning, the data may be coming and from frequently. So if a new key comes in and you want to insert a new key onto the array, it's not a good idea because you need a lot of memory moving. And for the ALDA things, you do not know what the non-zero, what to topic ID you have, and you do not create at the beginning. So if some word go to some topic, you create that things, but you do not know at the beginning. So you have a lot of key insert. In this case, maybe you want to use a key map, use a hash map solution. So I think this is a trade-off. These are two approaches. So next we discussed how we communication. That is communication over global keys. So each worker may maintain a global key to local ID map and use the local key during local computation. But if you do communication, yeah, you need to bring the global key so that everybody knows what this feature is. And we have discussed, okay, primary server use batch communication. That is why range-based solution work. I'll give you an example here. So we have 6 features, 2 servers. Each server maintains 3 features, and you have 1 worker. Worker only have 4 keys, so only a part of it. What this worker can be do is that you can say, okay, I want to push all this gradients, for example, within the key range 3 to 5. 3 and 5 is a global key you have. What you want to do that you first look at all these keys during your global key array, find the range and get what the range you have. You find okay, you only have two entries. You push that 2 entries to the server. Next, what you can do is that you can tell the server, I need all this model value from the key range 3 and 5. The actual thing you do is that you send the server the actual list that you have, which is 3 and 4, and the server will retain the same. So this communication API can at least you, for example, block gradient descent. Each time you have data block, and yeah, for generate gradient descent or HDD, you just choose the key range to a very large space. And on the extreme case, you can put the key range to 3 and 3. Just send 1 key each time. This is highly undesirable because you only send 1 key, and you need to pay the cost sending these things to the others, and a lot of TCP/IP packages, and send the things. So it's not a good idea. On general, you want to have a very large key, and you maybe send more than 1 kilobyte of data. What the data sent between machines are called a message. Message is quite simple. You have a product buffer header. It's about command. You maintain some command what the message is about, and timestamp you have, and a lot of other informations. And also you have a list of the keys. You have a list of values you want to send. The message, one message maybe split onto several ones because the worker maybe just want to, okay, I want to send something to all servers. On this case, sorry. On this case, yeah, you send to all these two servers here. So because you need to care about the fault tolerance. So only the system knows which server is alive and what the key range the server has. So that system will separate this single message into several ones. Each one goes to one particular server. Because it's a batch communication, you can do a lot of optimizations. I give 2 examples here. One that we find that between different iterations, you may send the key list again and again. For example, on the gradient descent, each time, each iteration, all the key you have is fixed because the training data is fixed. Each time you send the same key list to the server. So in this case, if you can cache, if at the first time the sender and the receiver both cache the key list, so that the next time the sender do not need to send the key list again. You just send the signature of the key list. Tell the receiver so I know you have been cached these keys. It tells you what the key list is, and you look up the key list on your memory, so I do not send it again. So this is immediately save about half of the space you want to communicate. The other thing that if your model is fast, that means you have an L1 required, for example. So most of the weight may be zeros. And you can have some user-defined filter. For example, we have shown yesterday, if the worker finds the current weight is 0, and I predict that this weight will remain 0 for the next iteration. So I can skip this one. I do not compute the gradient on this feature and do not send it, so that it should be a 0 here. So if you have a lot of zeros, what you can do is that you can use compression. For example, using Slappy, a very, very fast compression library. It's as fast as 1 pass of memory, but you can effectively reduce the size of the zero sense. And also you can do some, I think, for the Google Ads system using you can, because if the zero, the bit is 0, so you can have a different encoding things to re-encoding the things to reduce the zeros. So if you have a lot of zeros, you can do some optimization here to do not send the 0 sense. And because compression of doing the encoding things is much cheaper than sending the things over network, so it's a desirable way to do it. Next, I could give a quick overview of the system components, and I think it's necessary to. It's also some fundamental things if you want to implement a machine learning system. Once the system, the core system, once the application, that is what is the optimization algorithm you want, gradient descent, quadrant descent, and something. And once the parameters, that is a global shared data structure for the model. You can have, for example, we have been discussed, you can save as the sorted key value vectors, and also you can store as a hash map, and also you can have different data structures for different applications. We think that there's no single faster data structure for all these algorithms, so it's generally a good idea to have different things for different algorithms. And you have different loss functions, different penalty functions, and model. I think I can skip the details. Okay, this is what the things standing between machines. So we call this function the when. You can say them. You can carry some messages. So you have a L thread on this function, and you listen to your IP and listen to your port. If somebody tells you send you something, yeah, you get things and return to the system. And also the local system can send from this local IP to the other things. So to implement this thing, you have two options. One is that you can use a socket library. We use ZeroMinQ, so it's a friendly socket. In fact, it's a friendly socket library. I think nowadays people are quite interested in RDMA, remote direct memory access. That means if some guy sends some data to me, so the first thing that I go to the network card, then I go to the kernel, and then go to the user library, the user space. So you have to several things. What you can do is that you do not necessarily go to CPUs. The network card can read the memory directly and return the value. So you can reduce the latency between goes to the CPU, move to the register, move to the user space. And yeah, but it's quite limited. If you have a hash map and you change the memory structures, that all the things should be changed. But if you do not change things too much and you have an array, again, you can save reduce some latency. The second thing I think is worth to mention is that what is the thread model? Because it's not a single thread system. Because it's a synchronous system, you need to care about the thread you have. I'll give you an example here. So for the primary server, the whole system the core system is called post office because you can send some message for it. And all these things are called customers. For example, you have two customers, maybe it's a gradient descent, it's a linear algorithm, and this is the model you have. Each one has a thread. This one also has a thread. It's a receiving thread. So generally what you want to do is that the scheduler first tells all these working machines, okay, do iteration 1. What you do is that the scheduler sends a message to this machine. This thread will read the message for you and look at, okay, this messages goes to that customer. So I put the things onto the buffer here. The running thread of this guy will read the message here and look at, okay, this means do iteration. So I can call the function you have, that is computer gradient, sender gradient. How to send it? You put the message into the buffer and the post office will send it for you. And the only thing that you maybe need to call something back, for example, update something if the port value is coming back. What you can do is that because you do not want to wait it really come back, you must net this thread to do something else because it's a synchronous system. What you can do is that you tell the wait, okay, if something go back, you should run it. You give this one a function call. The next time, and if the port value is coming back, it still goes to the post office, and this time, okay, this message is for this guy and go to the buffer. This thread read the buffer, update its own data structure, and from that, okay, there's a function call. I must call because this guy tells me, and this thread will run the things. The only thing matters that what you need to care about which thread is running the function, because this guy can be running, this guy can be running. So if two functions called by different thread want to write the same data structure you have, you need to place a lock here. So this is something good because it's a synchronous system, maybe more efficient. The not so good thing that you need to care about, okay, this is a multi-step system. And the things maybe goes wrong if you do not guard your own data structures. Okay, so give a conclusion here. The kind of implementation supports extremely large model and is a synchronous system. It can be parallelized the CPU and the network. And it supports some flexible, consistent model. And you do some local ID to global feature ID to local feature ID mapping, so that you can write some program like a single thread MATLAB or like code. But the not so good thing that it's a little bit complex to understand it because you have multi-thread, and it's necessary to have an idea what a multi-thread system looks like, because if you want to have the faster performance, you need to have a good idea what the thread it is. Okay, so next I show you some demos. The first demo is that I just run on the training data using 64-bit features. So this is a feature ID, and this is a group ID. So each feature have about 100 features, and the feature ID group ID, this is a 0, 1 values, so I didn't store the value here. So okay, let's try it. I didn't go the EC2 this day because I run out of money, so just I have $10 at the beginning and the reference one and the referral guy, so I receive another $20 and I run a night. So let's go some small cluster of smallest cluster, and it's quite small. You have about 12 machines, and each machine CPU is not so good enough. The most not good thing is that the network is not so great. You have a very slow network. So here's the data. I first show you the data. Sure. Okay, here's a slightly large data than the previous data we have about. So this is each product data is about 1 gigabyte. You have about, I think it's about 1 minute examples on each part. So what I'm going to run is have about 24 parts. So each load will get 2 parts. So the only thing I need to change is I need to change the configurations. It tells which data you want to use. Okay, here I just changed the data from CTRA to CTRB. This is the only change I want to have. Next, I just run it. Okay, here is exactly as what I. Sorry, maybe you guys cannot hear it. Not true. Okay. I use npr run. It tells what the host that you have and create about 20 processes because I'm using 4 servers, 12 workers because I have 12 machines, and the server machine do not do very workload, so I can use every number I have. And each worker runs about 8 threads, and it tells what the application configuration you have. And okay, you can just run. It's a little bit slower because now you have about 21 megabyte training examples. The key range is now a general large number. It's an integer 64-bit number. The data is placed on a network shared file system. So you have about 30 gigabyte data, but because it's quite a slow machine, all these things are on a single disk. So you have 12 machines to read the things from a single disk. It's quite slow, in fact. So here's the network bandwidth you're using. And this is one machine. Because now you are reading the data. Okay, large number. Because okay, here's about the limits, the network limits of this machine. It's a small network card, and all these machines are read the disk from this single machine. So generally speaking, it's not a good idea. But if it goes to the distributed price, then it's okay then, because several things, because the data are placed on several machines, so we enjoy several bandwidths you have. Okay, so maybe I cannot wait. It's about 5-6 minutes. In fact, I have to do it. So this is, I just show you something I wrote before. Okay, here's the around about 1 hour ago. Okay, you load data using 10 minutes, as we have discussed before. Maybe you read data use the most of the time you have, if the data is not placed on the right place. And for the first iteration, you have about 600 minutes of features, and you use about 900 seconds. Because it's a sparse, you have a sparse equalizer, you can reduce the actual model size is not so large. And this is the KPD filter is a user-defined filter. That means I predict that feature should be remain on 0. I equalize. So the next iteration, the number of features and processes have been reduced to about 30 megabytes of data. And so that means the local communication tends to decrease, and also the communication decrease, because you only need to send so many entries, and you have compression and you have key cache, and you can reduce the network bandwidth. And for the rest of one is almost the same. So maybe it's not a good idea to test more things because it's quite slow. Okay, still not get done. Let's go here. So next, I want to show you how to implement a loss function. What I want to implement is a square hinge loss. So it's slightly different than hinge loss, because the hinge loss is not smooth on this point. So you cannot compute the gradient here. The gradient is not unique. What you can do is that you can have on this point you can use a square thing, so you have a smooth here. The bad thing that, okay, you place a lot of penalty here. The penalty you pay for very not classified good things goes to very large. But you enjoy it. You have it's a smooth function, and you have a second order gradient descent. What I want to implement is that how to implement this thing on the primary server. So in fact, it's quite easy. Several lines of code is enough. So you go to the loss directory, the loss. So you have, this is a general function of a loss function. So what do you want to have? You have two functions. One to evaluate the loss. The second is how to compute the gradient. And give the data you have, this is the data, this is generally a vector of matrix point, and this is the gradient you want to output. So basically you want to, because it's quite like a logit loss. So what do you want to do is that look at logit loss and copy them. Just to do a copy here. So it's the base function, the base class is a binary classification loss, and two functions you want to implement. One to evaluate. Given the label you have, given the x times w you have. So the array map is a very convenient thing, that the eigen map allows you pass it a point you have, tells it what the length you have, then they just give a whopper over your memory, so you can use in all the eigens operations. So I give the memory, I can do some operation for me, and I can manage the memory, because it's generally not a good idea to net icon to do all the memory management for you, because if you have a very large data, the icon may be copy a lot for you. So you have a lot of memory copy. If you want memory efficient, a good idea that you keep using this icon map class. So I just copy it and create a square loss. Oops. I changed the function name. And first of all, this is different as we have what the equation is. So u1 minus y times xw max eigen array the output 0. Give the length we want. And do square and do sum. Okay, here's the object function path. Next, you compute, because I only want to run gradient descent. I only want to compute the first order gradient. So this is it's not. So it's about x times, about 2 times x times sorry, how to compute that things. 1 minus y times x, this one. Okay, this is for if y minus y times t is greater than 0, then it goes to this direction. But if not, I need to, the gradient should be 0 and times if more than 0, it's greater than 0, that means y times t less than sorry, it's less than 1. So if it's less than 1, should be put this value into 0. Because for eigen3, this means it's the bool. This will return to your bool array, so you need to convert the tab and create cast. Okay, I think should be right. Okay, the next thing is that you need to test this system. You have increased the loss. You have added a loss here. The first step is add a configuration here. Go to proto configure.proto, and it goes to the loss configuration. Yeah, you need to. Okay, this is not. Okay, I already add this here, so you already have a tab here. But this is a product buffer type, so that you can add the configuration to your running. Next is if the configure tab equals to loss, I is not this one. Okay, this one. I return This is a pointer, it's a shared pointer. Return a new. Okay, it's done. Let's compile it. I didn't include the head file. Nonsense. That's not what it's meant. Never mind. Okay. Okay, it's not T here. I just popped the equation. One particular good thing is that if you're using this high-level math language, like it's less likely you have it's more easy to debug because you can compare with your equations. And this is true for MATLAB, for Python, but for C++, it's generally not good at, generally not easy to write a machine learning algorithm. So next I can run it. I change the gradient descent configuration. So that I use a different loss. I use a square hinge. And because square hinge you cannot start with a zero weight, because if it goes zero, the gradient should be remain zero. It will be remain zero forever. So you need to have a randomized initialization. Okay, that's right. Okay, it's not converged. The first thing you can do that you decrease the number of learning rate. Okay, so it's like too small. You increase it. Because I didn't add an adaptive grading here, I just use the original gradient descent. So yeah, this works. Looks like better. So it's almost done. For sparse data, maybe you still want to use adaptive gradient, even that for hinge loss, for everything. So another thing, I think it should be, if you're interested, it's a good idea to implement the hyperhinge loss. You solve the square hinge loss problem if the loss goes too small, the penalty will go to large because it's quadratic. Now the only change you have that you remove this non-smoothing by a smooth quadratic term here. So it works really great in practice. Next, as I conclude the whole tutorial, I think on this 5-day tutorial, we have discussed about industrial scale problem. We show what is computational advertising, how to get data, how to get the feature. So we usually get about 100 billion of examples, 10 billion of features, and the data size about 1 terabyte to 1 petabyte. So given huge data, the problem is not we do not have data, we do not have any algorithm. The problem is that we have limited machine resources. So the CPU is not so large, the machine is not so powerful, the network is quite limited. So this is a key question we have faced. Secondly, we introduced how to distributize several algorithms. For example, gradient descent and the corner-wise gradient descent and row-wise stochastic gradient descent. The latter two are very not easy to paralyze it. So lastly, we show how to implement a system scale to such large scale and how to use that system. And it shows some demo. I think nowadays, given the big data we have, given the current machine we have, I think on the coming few years, there should be a lot of research interest on the scalability, because we care about the computation, we care about the electrophy, we care about the running times. And on this data, I think distributed implementation, distributed computing is a very interesting one, because maybe on few years, it's not possible to a single machine scale to so large program. And so I think distributed computing is a necessary component. And for the next few years, I think there's a lot of hardware change, because the hardware also fit the workload. The workload also fit the hardware. So there's a huge opportunity to co-design of the system, co-design of the hardware, co-design of machine learning applications. So I hope this tutorial gives you a good idea, intuition what we have done, and what things is good at distributed computing, what things is you probably do not want to go down on distributed computation. So I hope I can give you some insight, some motivation, so you can do some great future work. And if you are interested, please talk to me so we can have work something together. So thank you. Questions or?
Are you going to share the slides?
Sure. Maybe I put on the website tonight.